Good day everyone, this is engineer Aljan Michael G. Sabak and I welcome you to our next discussion about Earth science. Last time we have discussed the interconnectedness of the four spheres and how it affects with everything in our planet. Now, let's go back from the start and discover the realms of time and space as we will fly back in time to know how the universe started, how it is originated, what are the different theories that talks about its origin and what will happen to it in the future. Primarily, the universe is the totality of space and time of the past, present and future with many galaxies that are spinning within its vastness. These are enormous collection of heavenly bodies held together by gravitational attraction that are light years away from each other. The story of how universe came to be is a fascinating contradiction. On the one hand, many things had to go just right for universe to turn out the way it did and develop. On the other hand, the formation of galaxies similar to our Milky Way is an entirely predictable consequence of the laws of physics, and it seems to have happened more than once. We will start with the story from the beginning, in the very beginning, and learn why generations of stars had to be born and then die explosive deaths before Earth could exist. We will look at what it takes for galaxies to form, and for objects to form alongside it, as well as why the nature of those objects depends on how far away from the central starting point they form. And when we say about the totality of space and time, it includes the structure of everything. The structure of everything includes the smallest unit in the universe up to the whole universe itself. Starting from the quarks, subatomic particles, neutrons, protons, and electrons, the atom, molecules, and matter. And these small units comprises the planets, our solar system, star clusters, galaxies, galaxy clusters, and lastly the superclusters. All in all, the structure of everything includes all of these things that forms our universe as of today. Say for example this Eagle Nebula. This Lobster Claw Nebula. We have also this Sol Nebula. And lastly our own Milky Way. All of these galaxies mentioned are governed by four fundamental forces. Without these forces, our universe won't be the universe as we see it today. And everything started in the beginning. But before let's move to the insights on how it began and evolved, let us first define and know more about our own universe. Let's start with the study of cosmology. Cosmology is the study of the universe, including its properties, structure, and evolution. And this science is governed by two different approaches and aspect. We call this paradigms. There are two paradigms, or interpretive frameworks, used to interpret the world around us, the conventional paradigm and the historical Genesis paradigm. Each has a different view of how long the Earth has been here, including the origin of the rocks, animals, and stars. Each sees the same data, but interprets it according to different historical assumptions. The Genesis paradigm interprets everything in light of the timeline and events recorded in the first chapters of Genesis. The conventional paradigm interprets everything according to the timeline and events constructed over the past 200 years as a replacement for the biblical history. The conflict between these two competing histories of the world is ultimately with respect to time. Now let's dive further into the realms of space and time. Let's further discuss the things we need to know of our own universe. There are four fundamental forces that governs the behavior of the whole universe. These are fundamental interactions. In physics, any of the four basic forces, gravitational, electromagnetic, strong, and weak, that govern how objects or particles interact and how certain particles decay. All the known forces of nature can be traced to these fundamental interactions. Gravity is a property of mass and it attracts to bodies and light responds into it. It reshapes between space and time, and also it acts between objects and mass. Electromagnetic force includes the interactions of charged particles and is responsible for all surface interactions of matter, and it binds atoms together. Strong nuclear force, on the other hand, holds and binds protons and neutrons together in the nucleus of the atom, while the weak nuclear force is responsible for nuclear radiations and fission that can be found in radioactive decay. Only about 4% of all the mass and energy in the universe is matter with which we are familiar here on Earth. Most ordinary matter consists of hydrogen and helium located in interstellar and intergalactic space. Only about 0.5% of the critical density of the universe is found in stars. Dark matter and dark energy, which have not yet been detected in earthbound laboratories, account for 95% of the contents of the universe. When we say about dark matter, it refers to exotic matter that interacts only weakly with ordinary matter. While no such matter has ever been directly observed in the laboratory, its existence has long been suspected. While dark energy, bizarre form of matter, or perhaps a property of the vacuum itself, that is characterized by a large, negative pressure, repelling force, can cause the expansion of the universe to accelerate, or speed up. Now let's have a full discussion on the conventional paradigm that talks about the Big Bang Theory as its origin. So, what is really the Big Bang Theory? According to the Big Bang Theory, the universe blinked violently into existence 13.77 billion years ago. The Big Bang is often described as an explosion, but imagining it as an enormous fireball isn't accurate. The Big Bang involved a sudden expansion of matter, energy, and space from a single point. The kind of Hollywood explosion that might come to mind involves expansion of matter and energy within space, but during the Big Bang, space itself was created. The Big Bang Theory was first proposed by the Belgian priest Georges Lemaitre in the 1920s. The framework for the model relies on Albert Einstein's general relativity and on simplifying assumptions such as homogeneity and isotropy of space. This theory explains the origin of the universe and suggests that the universe, our solar system included, is part of an expanding system where all galaxies are moving farther away with each passing day. As you can see from the image, it started unknowingly and continued to expand throughout time. This is a 3D image of the universe from the beginning and how it is evolving in the present. It is continuously expanding as we speak. At the start of the Big Bang, the universe was too hot and dense to be anything but a sizzle of particles smaller than atoms, but as it expanded, it also cooled. Eventually some of the particles collided and stuck together. Those collisions produced hydrogen and helium, the most common elements in the universe, along with a small amount of lithium. Then 20 billion years ago, an explosion hurled this material in all directions and continuously expanded. After which, gases cooled and condensed, forming stellar stars systems that we call galaxies. 20 billion years in the future, the expansion will stop and gravitational attraction would follow, where stellar material will collide to form a new hot, dense fireball, and the process starts again. Now, let's do it step by step so that we can understand it more. First, and in the beginning, the Big Bang was not an explosion in space. Instead, it was the appearance of space everywhere in the universe from the primordial fireball. When the universe was very young, it underwent an incredible growth spurt. During this burst of expansion, which is known as inflation, the universe grew exponentially and doubled in size at most 90 times. After inflation, the universe continued to grow, but at a slower rate. As space expanded, the universe cooled and matter formed. For the first 380,000 years after the Big Bang, however, the intense heat from the universe's creation made it essentially too hot for light to shine. Atoms crashed together with enough force to break up into a dense, opaque plasma of protons, neutrons and electrons that scattered light like fog. About 380,000 years after the Big Bang, matter cooled enough for electrons to combine with nuclei to form neutral atoms. This phase is known as recombination, and the absorption of free electrons caused the universe to become transparent. Roughly 400 million years after the Big Bang, the universe began to come out of its dark ages. This period in the universe's evolution is called the Age of Reionization. Clumps of gas collapsed to form the very first stars and galaxies. In these age of expansion, more stars and galaxies are formed. After which came the birth of our own solar system that includes our sun and the planets. Lastly, the universe will continue to expand. You may wonder how a universe can be created out of nothing, or how we can know that the Big Bang happened at all. Creating a universe out of nothing is mostly beyond the scope of this chapter, but there is a way to think about it since as far as we know, the Big Bang really happened at all. There are very good reasons to accept that it is indeed how our universe came to be. We now have tools that are powerful enough to look deep into space and see the arrival of light from early in the universe's history. Astronomers can detect light from approximately 375,000 years after the Big Bang is thought to have occurred. Physicists tell us that if the Big Bang happened, then particles within the universe would still be very close together at this time. They would be so close that light wouldn't be able to travel far without bumping into another particle and getting scattered in another direction. The effect would be to fill the sky with glowing fog, the afterglow from the formation of the universe. As a summary of the happenings in the Big Bang timeline, we have this on the image. Everything started with a bang. 1. The cosmos goes through a superfast inflation, expanding from the size of an atom to that of a grapefruit in a tiny fraction of a second. 2. Post-inflation happened and the universe is a seething, hot soup of electrons, quarks and other particles. 3. A rapidly cooling cosmos permits quarks to clump into protons and neutrons. 4. The universe in this period is still too hot to form atoms. Charged electrons and protons prevent light from shining. The universe here is a superhot fog. 5. Electrons combine with protons and neutrons to form atoms, mostly hydrogen and helium. Light can finally shine on this age. 6. Gravity makes hydrogen and helium gas coalesce to form the Geon clouds that will become galaxies. Smaller clumps of gas collapse to form the first stars. 7. As galaxies cluster together under gravity, the first stars die and spew heavy elements into space. Those will eventually turn into new stars and planets. There are several independent pieces of evidence that support the Big Bang theory. These are the evidences. 1. Cosmic background radiation. 2. Composition of the universe. 3. Age of stars. 4. Redshift data. The first evidence we have is the cosmic microwave background radiation. This is exactly what we see when we look at light from 375,000 years after the Big Bang. The fog is referred to as the cosmic microwave background, or CMB, and it has been carefully mapped throughout the sky. These temperature changes were evidence of the heat left over from the Big Bang. The early universe should have been very hot. The cosmic microwave background radiation is the remnant heat left over from the Big Bang. The map displays the cosmic microwave background as temperature variations, but these variations translate to differences in the density of matter in the early universe. The red patches are the highest density regions and the blue patches are the lowest density. Higher density regions represent the eventual beginnings of stars and planets. According to the Big Bang theory, the universe was originally just energy. As the universe expanded, that energy should have cooled, some would have turned into matter. That cooled energy should still be found throughout the entire universe, with small fluctuations found throughout. The Wilkinson Microwave Anisotropy Probe (WMAP) and the Planck Space Probe have measured small fluctuations differences in the cosmic background radiation (CBR). These differences were imprinted on the background radiation from tiny fluctuations in the quantum energy of the original expanding universe. The Big Bang theory predicts these differences, and these probes have discovered them. By measuring the size of these clumps, you can calculate the age of the universe with great accuracy. This gives an age for the universe of 13.8 billion years. Here we have the image transformation from the first sighting of the cosmic background microwave radiation to the latest image mapped by the Wilkinson Microwave Anisotropy Probe. Both three are simulations of the radiation, and technology has been there to provide us clues to our universe. Another piece of evidence comes from the abundance of the elements we see in the universe. For the Big Bang to be accurate, the simplest elements would have been the first to form, and all heavier elements would have come from nuclear fusion inside stars. When astronomers look at the elements in the universe, we find that the identifiable matter in the universe is mostly hydrogen. This matches the predictions made by the Big Bang. In fact, measurements show that the universe is 74% hydrogen and 24% helium. In order to create this much helium from nuclear fusion, the universe would have to be at least 12 billion years. Third, as we have the age of stars. The universe cannot be younger than the oldest stars. Stars form in different sizes, usually from the collapse of a nebula or cloud of dust and gas in space. The larger stars fuse hydrogen into helium at a tremendous rate, and die as supernova explosions after only a few million years. Smaller stars take longer to use up their hydrogen. Some stars, such as our Sun, have formed partly from the exploded remains of older stars. The oldest stars are among the smallest, and are called red dwarf stars. Estimates of the age of the oldest red dwarfs give an age for the universe of at least 13 billion years. And last we have Edwin Hubble. Edwin Hubble justified Lemaitre's theory through his observations that the universe is continuously expanding. Galaxies are moving away from each other. By studying the spectra produced by galaxies throughout the universe, we can identify that most objects are moving away from each other and that the universe is expanding. Through Hubble's law, which is the rate at which a galaxy is moving is directly proportional to its distance from us. In other words, the farther away a galaxy is from us, the faster it travels away. And if you know how fast the universe is, you can calculate roughly how long ago the universe began for it to reach its current size. This gives us a universe that is at least 12 billion years old. The redshift basically is the shift in the expanding wavelengths of light toward the red color, so if you see a moving object away from way, you will see wavelengths towards the red color. And this redshift suggests that space itself is expanding. That implies that at some point the universe was smaller. To further visualize the redshift, let's look at the image. Here we can see the changes in wavelength towards the red color of some galaxies observed from the Earth as the distance is getting farther away. All four of these lines of evidence, along with the Hubble flow and the abundance of the light elements, agree with each other, and together form the pillars of modern cosmology. Our estimate of the age of the universe has improved greatly just in the last 2 decades. From all this evidence, we have solved one of the great mysteries of the universe. But consequently, there are limitations of the theory, and that is why it remains a theory. Big Bang limitations. The following are the limitations of the Big Bang theory. Monopole structure in the universe. The Big Bang theory predicts the production of heavy stable magnetic monopoles in the early universe. However, no magnetic monopoles have been observed. Makes no attempt to explain how structures like stars and galaxies came to exist in the universe. Horizon fluctuations in the CMB radiation. temperature of the CMB is observed to vary slightly across the sky. Based on the Big Bang expansion, distant regions of space in opposite directions of the sky are so far apart that they could never have been in causal contact with each other. However, the evidence showing the uniformity of cosmic microwave background temperature shows that these regions must have been in contact with each other in the past. Flatness. The Wilkinson Microwave Anisotropy Probe (WMAP) revealed the geometry of the universe to be nearly flat. However, under the Big Bang theory, there should be curvature as time grows. Inflationary universe. This theory still is untested as we speak. Overall, the universe is very vast and we haven't seen all of the things in it. We might not know what will happen in the future, but thankfully it was created. The universe that remained in the past is our very own universe as of today, and it will likely be the same universe in the future. That's all for this session. See you on the next video.